Okay, so we are looking at logic and reasoning, and we are looking at propositional logic. So, just to do a quick recap, we first looked at the language, and the language is made up of a set of propositional symbols. Um, I do not remember what the symbol we use anyway. So, something like this, a countably infinite set of atomic symbols, and each of these symbols stands for a sentence, and we do not particularly care what it stands for essentially. And associated with this set of symbols is a function v, which maps p these symbols to the set let us say true and false, basically a 2 valued set, which as far as we are concerned will stand for true sentences and false sentences. And then we had connectives, and, or, not, implies, and so on, which gives rise to a set of sentences. So, we will call them the set of formulas. Let us call the set F. So, we could construct compound sentences from the atomic sentences using the logical connectives, and associated with this set of formulas is a function val, which maps F to the same set true or false. So, this side is a syntax and that side is in some sense the semantics of this thing, and what the semantics captures here is that how do these logical connectives connect the or influence the meaning of compound sentences essentially, and that is given by this. So, if you remember, for example, a sentence like P and Q would map to true if both P map to true and Q map to true, and so on and so on. Now, given a sentence F belonging to F or formula F belonging to F. So, for example, you might say something like P and Q implies R, or not P implies S, some such formula, any arbitrary formula which can be constructed using these logical connectives. P, Q, R and S are the atomic sentences, and implies or and not implies other connectives. We can find a valuation for this if we know what is the valuation for P, Q, R and S essentially. So, if we know, for example, that P is true and let us say P, Q, R, S everything is true, then this true implies true or false implies true. So, this whole thing will evaluate to true essentially. So, this was the notion of truth. This is the notion of truth that we which says that given a sentence F belonging to this set of sentences F, we can compute whether the sentence is true or not. Given a sentence and given a valuation V for all the atomic sentences, we can compute whether the given sentence maps to true or false essentially. Then I do not remember whether we discussed this, but in general a formula can fall into 3 categories. One is a valid formula. So, we say F is valid if for every valuation V that we can think of, val F is equal to true. So, you are familiar with this notion, we are just repeating this. So, when we say for every valuation V, essentially we are talking about the truth table for the formula. So, for this formula for example, we can construct a truth table which will have 16 rows, because there are 4 propositional atomic sentences, which means P can be true or false, Q can be true or false, R can be true or false, and or S can be true or false. For each of these 16 valuations or each of the 16 rows in the truth table, if the last column is labeled with true, then we say that the sentence is valid. So, a sentence is valid if it is true for all possible valuations. A trivial sentence which is valid is, for example, P or not P. This is of course, there is only one variable, but this is a valid sentence, also known as a tautology, always true. We say that a sentence is satisfiable or a formula is satisfiable if for some valuation V this is true. The same thing, except that instead of every we use the term some, that if you can find at least one valuation which will make this true, then that sentence is satisfiable. For example, I might say P implies Q, one simple sentence, not always true. For example, if P were to be true and Q were to be false, this is false, but I can find valuations for P and Q which will make this true. In fact, there are 3 valuations which will make this true. Such sentences are also sometimes called contingent sentences. And so, one is valid, the second is satisfiable or contingent, and the third is unsatisfiable. Here we replace this with no. If there is no valuation which makes this sentence true, then it is unsatisfiable essentially. An example, as you can imagine, is something like P and not P essentially. So, in general there are 3 kinds of sentences: valid, satisfiable and unsatisfiable, and all the 3 notions are used somewhere or the other, as we will see later essentially. So, when we talk about truth, we also say we use this symbol to say that a formula is valid. We can say using this essentially. Then there is a notion of entailment. Okay, now, this is an interesting notion, because when we study logic, the reason we study logic is to be able to capture valid forms of argument essentially. We are not so much interested in saying can we find a valuation which will make the sentence true or not. We are more interested in saying that if somebody has given you a set of premises or a set of axioms, then does some other sentence follow from that essentially. So, given a set S of sentences, we say that a formula F is entailed by S which we write as S entails F if the following is true: if for every that makes S true, and when we say a set of sentences is true, essentially what we mean is that every sentence in that set is true. So, you can think of it as a bigger sentence with the and sign in between them essentially. So, we are more interested in the notion of entailment, that okay, somebody gives us a set of premises, let us call them S, then we want to ask whether a given formula F is true or not essentially, and that is a notion of entailment essentially. So, these concepts are kind of semantic concepts. On the other hand, we have the notion of provability. So, if you recall, we did a small proof in the last class. Notion of probability is tied up with a set of rules of inference. For example, the most commonly used rule of inference called modus ponens can be expressed as follows, that if you have alpha and if you have alpha implies beta, then this entails beta. So, last time we wrote it as 3 separate lines, alpha and then alpha implies beta below and then beta, but this is just another way of writing it. Essentially, you are saying that if you are given alpha and if you are given alpha implies beta, then you can derive beta, or in some sense you can add beta to your set of sentences. So, the notion of provability is a, or the notion of proof is an entirely syntactic concept. It simply says that given a set of formulas, you can keep adding new formulas to the system, and this particular rule says that if you have a formula which matches alpha and if you have another formula which matches alpha implies beta, then you can add the formula which matches beta to the set essentially. This alpha and beta could be arbitrarily compound formulae, they do not have to be atomic formulas essentially. It is just as a pattern, that a pattern, the same thing must be here of course. Alpha can be any formula, and but if that formula implies beta is present in the database or knowledge base or the set of sentences, then you can add this. So, the proof finding algorithm is basically a simple algorithm which does the following: select a rule of inference, select some data to which you will apply it to, and add some new formula to your database, and you keep doing this repeatedly till you have proved the formula that you are interested in essentially. So, another rule of inference is, for example, modus tollens, which says that if you have not beta and alpha implies beta, then you can add not alpha to the set. I am sure you are familiar with this kind of formulas. So, the next question we want to ask is, what makes a rule of inference a suitable rule of inference essentially. So, if you recall, we had these notions of soundness, we say that a logical system is sound, which says that if S in other words, if you can derive a formula alpha from a given set of sentences S, then if your logic system is sound, then that alpha will also be entailed by the set of sentences S, okay, which can be expressed as the following, that if your set of premises are true, then the conclusion will necessarily be true. That is the notion of entailment. The thing on the right hand side is the notion of entailment. We say that a rule of a logic system is sound if anything that can be derived is entailed as well, and on the other hand, a logical system is complete if anything that is entailed can be derived. Observe that these also look like sentences in a logic, but this is a slightly different logic in which we can talk about sentences like S derives alpha or S entails alpha, which of course has to be in some different logic essentially, not in propositional logic. So, the question we want to ask is, when is a rule of inference sound essentially? So, soundness is tied up to valid rules So, a rule is valid if it entails the right hand side. So, a rule like this is valid if this and this actually entail beta essentially. So, let us look at an example of a rule which is not valid. If I say alpha implies beta and beta, then I say alpha. I am just writing it in the old notation, it says, but it's similar thing. This is not really a valid rule, so we do not have a name for it. This rule says that if alpha implies beta is given to you and beta is given to you, infer that alpha is true. And I do not know whether we discussed in the last class, this is actually the process of abduction. So, it is like this, for example, you might say that if somebody is drunk, then that person staggers while walking. So, that could be alpha could stand for somebody is drunk and beta could stand for the person staggers while walking essentially. And then you say somebody is staggering while walking essentially, and you come to the conclusion that the person is drunk essentially. Now, this is not a valid rule of inference, because it is possible that the person may be drowsy or sleepy or tired or hurt, it could be anything, but it is not necessarily follow that if you have this fact, you assume that to be true, that people who are drunk will stagger, it does not mean that anybody who staggers is drunk essentially. Whereas, if you were to use that formula here, if you say that somebody is drunk and if you have this rule that somebody is people who are drunk stagger, then you can infer that the person will stagger, because the rule actually says that essentially. Or another example that we might have discussed is this process of diagnosis. In medical diagnosis, disease causes symptoms. So, disease implies symptom. If you see the symptom, then you infer the disease actually. Now, that is not necessarily a valid inference, because it is possible that the symptom could have been due to some other disease as well essentially, because there are many diseases which, for example, cause fever. Then if you simply say that just because it is fever it is this particular disease, it is not a valid rule of inference. So, how do we distinguish between valid rules and rules which are not valid? Valid rules are based on tautological implications. Which means that corresponding to every rule of inference, there must be a tautology, which is there must be an implication statement which is a tautology, and corresponding to modus ponens, for example, the tautology is alpha and alpha implies beta implies beta. So, notice the similarity between that pattern and this pattern. Here this is one sentence in my language of logic. There I am using an additional symbol which stands for derives or something like that, which is an extra logical symbol, in the sense it is not part of the language that I am using, but this is a sentence in my logic. And what we are saying now is that a rule of inference is valid if it is based on a tautological implication, and by this we mean we should have a corresponding sentence here, and the sentence must be a tautology. So, is this sentence a tautology? You can construct a truth table to find out and show that this is indeed a tautology essentially, or you can try and show that this is a tautology by trying to show that it is not a tautology, which is the kind of proof that you often do, proof by contradiction, which would say, okay, let us say that can we make the sentence false. Now, if you remember the truth table for implication, you can make it false only if you make this part true and if you make this part false essentially. Now, you can make this part true only if you make this true and if you make this true. To make this true, you have to either make alpha false or beta true. But if you have made alpha is true here, so this means alpha is true. So, now alpha has become true and beta has become false. So, this part becomes true implies false, which is actually false. Once this becomes false, this and this becomes false, and once this and this becomes false, this becomes true. So, we can make the sentence false essentially. Sorry, we cannot make the sentence false, because to make that sentence false, we have to make this part true. We have to make this part true, but we are unable to make this part true, because you have to make this true and this part false. That is the only row in the implication truth table where this implication formula becomes false. So, this has to be false. So, that means this beta has to be false. Now, to make this whole part true, this alpha has to be true. So, to make this part true, true implies false has to be true, but true implies false is not true, it is false. So, we are not able to make this false. So, we are not able to make this whole sentence false. So, this sentence is a tautology. So, as a small exercise, maybe you should just construct the truth table for this and see that this is indeed a tautology. Now, there are other kinds of rules of inference which are based on tautological equivalences, and they give rise to rules of substitution. These rules of inference have a sense of direction, in the sense that you have to be given the stuff on the left hand side, and then you can produce the formula on the right hand side essentially. So, it has a sense of direction, you can go from left to right essentially. In rules of substitution, you say that two formulas are logically equivalent, and therefore, you can substitute one for the other at any point of time essentially. So, an example of a rule of substitution is, and you must be familiar with many rules like De Morgan's laws and so on, but one rule is, for example, alpha implies beta is equivalent to not alpha or beta. So, you must have looked at it at some point. If you have not, then just try to construct a truth table for this, and you will see that this is indeed a tautology. And if it is a tautology, we can base the rule of substitution on this, which means that whenever we see a pattern of the kind alpha implies beta, we can replace it with the pattern of the kind not alpha or beta, and vice versa. And we do not have to replace it, in the sense we do not have to substitute it, we can even add it, but it amounts to the same thing essentially. So, De Morgan's laws, for example, you must have studied this thing. So, there are many tautological equivalences, and you can convert each of them into a rule of substitution. You can also see a rule of substitution as a bidirectional rule of inference, which says that this implies this and that implies that, because if you might remember, you can say something like alpha to beta is equivalent to alpha implies beta and beta implies alpha. So, you can think of a rule of substitution as two rules of inference essentially, both going in both the directions essentially. So, what you have in your armory to construct a logic machine is a set of rules of inference, a set of rules of substitution, and your task is now to pick one of these rules and keep producing new formulas till the formula that you are looking for is generated. So, till this formula f that we are interested in is generated essentially. So, if you remember the example we did last time, we had something like this, that it was given to us that P and Q, where P was something like Alice like maths and Alice likes music or something like that. Then P implies R, then R and S implies T, then not Q or S and from this you have to show T. That was the problem that we looked at last time or something very close to this. So, these are the 4 premises given to S, the set of sentences S, and from this we have to show that T is derived essentially. So, we write this as this, which says that this and this and this and this. So, if let us say this is S1, S2, S3, S4, then S1, S2, S3, S4 entails this or derives this. We can only use the 2 terms interchangeably, entailment and derivation, if the logic is both sound and complete essentially. If it is sound, then whatever is derived is true, is entailed. If it is complete, then whatever is entailed must be derived. So, we will come to completeness in a moment, but so far we have addressed the issue of soundness. When is my logic machine sound? Provided I use valid rules of inference, and the valid rules of inference are characterized by tautological implications or tautological equivalences, and corresponding to each tautological implication we can construct a rule of inference. So, for example, if somebody says P implies P is a tautological implication which is trivially true, you can have a trivial rule for this which says that if you have P you can add P to the right hand side, but of course, that is trivial. For any tautological implication you can add a rule of inference, for any tautological equivalence you can have a rule of substitution essentially. So, before we move on, I want to mention one theorem which is quite well known. So, let me write it here. It is called deduction theorem, you should look it up. This theorem says that if I have a set of sentences S and a sentence alpha, and I want to derive the sentence beta, if I can do that. So, remember that this notation stands for this idea of generating a proof, that you keep applying rules of inference till you generate beta essentially. The deduction theorem says that if you can do that, then it is always the case that you can do this. You can take S to the right hand side, sorry, you can take alpha to the right hand side, and instead of deriving beta, you can derive alpha implies beta. Now, this S could be an empty set, okay, which means that if you want to show that beta can be derived from alpha, then you can equivalently show that this formula alpha implies beta is true. So, in other words, if you want to show that this is true, this implies, this amounts to showing that this and this and this and this implies this. If I construct a large formula, then that is true or a tautology. So, you can see that all valid derivations amount to proving these large tautologies actually. So, let me ask a question, what is the relation between these 3 kinds of sentences? Can you think of a relation? If f is valid, then if f is satisfiable, or if f is unsatisfiable, is there a relation between them? We will come to this, just think about that a little bit. So, I want to spend a little bit of time talking about completeness. When is a logic system complete? So, you can see that by definition a logic machine or a logic system is complete if it can derive every true formula, or in other words every formula that is entailed by a given set of axioms essentially. And in the last a couple of 100 years ago, there were a lot of people trying to build logic systems and show that they are complete essentially. So, these are known as axiomatic systems. Axiomatic system said there is a set of statements you must accept to be true without asking about them, or just accept them to be true on faith, and some rules of inference of choice is made essentially. So, one of these earlier systems, in fact probably the first one, was given by Frege, who is also credited with inventing first order logic, or the modern form of first order logic that we use. He had 6 axioms which were as follows. This is the name of the axiom, then one, it says alpha implies beta implies alpha, then if you just look up for Frege's axiomatic system, you will find a very nice page on Wikipedia which describes these 6 axioms and the things which follow from there essentially. So, you do not have to write them here. Okay, so, this Frege gave this axiomatic system which has these 6 axioms. The first axiom says alpha implies beta implies alpha. The second axiom says alpha implies beta implies gamma. The whole thing implies alpha implies beta implies alpha implies gamma. The third one says alpha implies beta implies gamma is also the same as beta implies alpha implies gamma. Then there are 3 axioms which use the negation sign. Alpha implies beta implies not beta implies not alpha. So, you can see for example, this one FRG1 has a connection with these 2 rules essentially. This rule says that alpha implies beta, and if you see that not beta implies not alpha is implied, then if you were to replace this with not beta implies not alpha, then you have something like modus tollens essentially. So, you can see that modus tollens can be derived using FRG1 essentially. You substitute this with not beta implies not alpha, and that then it becomes like modus ponens, because not beta is given, not beta implies not alpha is given, and not alpha is will be given. And this, which for many of us is trivial, negation alpha implies alpha, is a axiom in Frege's system essentially. And he had one rule of inference which was modus ponens, which we are familiar with, this rule here. So, Frege's axiomatic system says that all tautologies of propositional logic can be derived from this set of axioms and this rule of inference. So, it is a complete system. Of course, we are not going to go into a proof of this here, but we will just take it for granted that here is a definition of a complete logical machinery. And after Frege, there were many people who devised different axiomatic systems using different sets of rules of inference and other things essentially. Now, as a small exercise, I will ask you to prove this formula using Frege's axiomatic system. Observe that this is not taken for granted in Frege's system. When you say an axiomatic system, these are the only 6 sentences that you take for granted. These are patterns, which means alpha can be substituted with anything essentially, and only one rule of inference is allowed. Using this, can you come up with a derivation of this sentence P implies P? You can try it a little bit while, and then if you can't succeed, you can go to the Wikipedia site and you will find a proof there. So, I am not going to do it on the board here, but you can find the proof essentially. But the whole idea of developing axiomatic systems was to choose a set of axioms in the given language, which is in our case propositional calculus or propositional logic, a rule of some rules of inference, and say that this is a set which is complete, which means all tautologies can be derived in this, including this tautology which stands for this and this and this and this implies this. If you look at the deduction theorem, that if I can show that to be a tautology, then I can show that this T follows from those 4 sentences, it is equivalent, right. So, if I can show this, then I can show that beta follows from alpha essentially, and Frege's system can derive all possible. Of course, that does not mean that it is a trivial task. So, as you know, people have been struggling to find proofs of things. For example, Fermat's last theorem took a few 100 years before it was accepted as being solved essentially. So, finding the proof is not a trivial task, it is because there is a lot of choice available to you what to use and so on. So, one the kind of proof that we did in the last class is called natural deduction, which says you take a rule of inference, apply it to some premises and add a new one to the set, and then again take another rule and apply it, and so on and so forth. So, we had, if you remember, we had said that from this we can first derive P, and then from P and R we can derive R, and then from P and Q we can derive Q, then from Q and not Q or S we can derive S. There is a rule which I have not maybe not stated. So, from R and S we can derive R and S, and from this we can derive 3. So, there is a you can start like this, derive all these things and then derive T. This process is called natural deduction essentially. Very often we can generate rules of inference by showing something like this. Supposing I want to show that this is a tautology, then one way of proving things is to assume the left hand side. So, I assume P and Q implies R, and in some sense put it in a box. So, everything that follows within the box is based on this assumption. Then I make another assumption P, I open another box, and a third assumption Q, in which I open another box, and now I can say, so I have assumed these 3 formulas, I have assumed this, I have assumed this, I have assumed this. Now I can say P and Q, then I can use P and Q and this and apply modus ponens and assume R, or infer R rather. Then I can close this box and say, okay, I had made this assumption of Q, and so it is a little bit like this application of this deduction theorem, that I am closing this box and I am saying now Q implies R, because R is what I deduce from here. Then I am saying I will close this box and I will get, let me write it here, P implies Q implies R, and then finally when I close this box, then I have this implies this. So, you see to prove this formula. So, you must be familiar with this kind of a proof which you have done quite often. Assume that this is the case, then show that something is true. So, to show that this is a tautology, we said let us assume the left hand side, then we said let us assume P, then we said let us assume Q. So, we have 3 assumptions depicted by these 3 boxes. So, anything that is entailed by the assumptions are inside the boxes. So, P and Q is true inside this box, because Q has been assumed, P has been assumed, and because this has been assumed, R can be inferred, because P and Q implies R, modus ponens we can apply. Then we close this box and we get Q implies R, because the only assumption we made in here was Q. Then we close this box and we get P implies Q implies R, because the assumption we made was P here, and then we close this box, we get this formula essentially. So, that is another way of another rule of inference essentially. So, the process of finding proofs is not a straightforward process, and a lot of people spent a lot of time trying to devise strategies for finding proofs. And in 1965 along came a logician by the name of Robinson, who devised a schema which we will look at in the next class, in which only one rule was of inference was enough for deriving all kinds of things essentially. Now, observe that when we talk of axiomatic systems, we are really talking of proving all tautologies essentially. In the real world, we are often more interested in showing that given a set of premises that something else is true. But before we go on to this Robinson's method, there is another observation we must make, which is about the choice of connectives. Okay. Now, if you observe this Frege's system, it uses only 2 connectives, the implication and the negation essentially, and yet Frege made a claim that his system is complete, which means any true statement that can be expressed in propositional logic can be derived in this essentially. So, where do the other connectives come from? Well, you cannot derive statements in those exact forms, but we have these rules of substitutions essentially. Okay. So, for example, we have this rule of substitution which says that not alpha or beta is equal to alpha implies beta. So, Frege is saying that not that he can derive this form of the sentence, but an equivalent form of the sentence here essentially, but logically they are the same, they are saying the same thing essentially. So, there is a notion of a set of connectives also which is complete, and I am sure you are familiar with this set. So, I am not going to spend too much time here. So, for example, you might say that this set, so Frege said that this set is complete, just use the implication sign and the negation sign, and you can express everything that can be expressed in propositional logic using these connectives, because we have all these rules of substitution, and you can derive everything that is a tautology in propositional logic using his system of derivation, which is those 6 axioms plus the modus ponens rule essentially. But there are other systems which are complete. So, for example, a commonly used system uses these 3 signs, negation, and or, and we will see that Robinson's method uses this set of connectives. You can even just work with and, or you can even just work with or and negation sign, and there are other combinations which are possible, and some that you might be familiar with is NAND and NOR. So, you must be familiar with the fact that these 2 connectives, not and not or, NAND and NOR, this one single connective is enough to express everything you can express in propositional logic, which means you choose any set of connectives that we have here, and or implies equivalence and so on and so forth, express anything using those connectives. You can devise a language in which there is only one connective NAND or only one connective NOR, and you can express the same thing in this logic with only one connective. And what do you mean by, you can express the same thing, you mean that they are logically equivalent, which means that any valuation which makes any sentence true in the first one will also make the second sentence, the same sentence true in this second formulation. In other words, if alpha implies beta is true here, not alpha or beta will be true here, or if this sentence is true, then this sentence, that is the meaning of equivalence, right. So, anything that can be said in propositional logic can be set with a set of complete sentences, complete connectives, and then you can choose a set of axioms and a rule, some rules of inference, and you can have a logically complete system. The beauty about Robinson's system was that he did not need any axioms, he just needed one rule of inference, and that was a complete system. You could derive everything, all tautologies in that essentially. So, as a last thing, it is nice to define a complete system which is minimalist in some sense, it uses a small set of axioms and a small and one rule of inference, but as you will see if you try to show this P implies P, it involves a lot of steps in showing that P implies P, because you have to start with some axiom, substitute something for there, and then keep playing with the axioms. It is a nice exercise, you must try. In practice, you would not want a minimalist system, you would want a system in which inferences can be made very quickly, which means you can derive sort of complex rules of inference. So, you can say for example, that and this fact, in fact, this is a rule of inference, that if alpha implies beta and beta implies gamma, then alpha implies gamma. You can have a rule of inference like this. So, it is, you can see it is like transitivity, if alpha implies beta and beta implies gamma, then you have a rule which says alpha implies gamma. If you have such a rule in your system, then if you have to show alpha implies gamma or something like that, or if somebody had given you alpha and asked you to show gamma, then you can just take this rule here and this conclusion here, and then use modus ponens and derive gamma essentially. So, it makes sense to introduce more rules of inference, which would make your inferences shorter. So, there is some vague analogy with defining a language here. So, when people define the instruction sets for machines, they work with more instructions or less instructions, and each has its advantages essentially. Okay. So, theoretically of course, it is nice to show that a small set is good and complete, but in practice you may need something bigger, unless you come up with something like Robinson's method, which was small and yet very efficient essentially. So, we will look at Robinson's resolution method in the next class essentially.